Okay. Mass spec. Yeah. What? We will be. Well, we're doing a little bit of both. Ah! I don't know. I'm trying to get this file to open, and it's like the circle is spinning, and it's making me sad. Open. Why is this so hard? Why won't it open? Okay, here we go. Shh. All right. So, I wanted to check with you guys on number 12 because I'm looking at this and I'm like, how did we feel about number 12 on the mass spec? Oh, crash report for Adobe. Don't send. I don't care. Was it good, number 12? Okay. So I look at it and I'm like, if it's 39.9, yeah, but regardless, that should be calcium, n'est-ce pas? Oh, hang on. Oh, yeah, argon. That is so bizarre. Oh, it's one of those ones where argon actually has a higher molar mass than potassium, which is why I thought, oh, it must be calcium because that's the closest one. Potassium's lower than that. So yes, it is argon because that's its actual mass. No, we're good. Argon is good, but I was confused by the whole potassium thing, so yeah. Yes. Okay. What are we talking about? This is in the what's-he-woo? Is this in the photoelectron spectroscopy review? Okay. Actually, you know what? I feel like the fastest way to get at this, no, I don't. Oh my God. Would be to go to here. Okay. Here we go. Okay, what number? 20. Number 19 and 20 refer to the photoelectron spectrum for phosphorus. Oh, they spelled phosphorus wrong. That's really irritating. Shown below. Compared to the 3p peak on the PES for phosphorus above, a PES chart for sulfur should have a 3p peak width. So we've got phosphorus, which is 3p3, right? And so sulfur would have a 3p peak. It needs a higher intensity, yes, because it's got more electrons on it. And I think we've discussed this one to death now, like the phosphorus and sulfur one, in that this electron repulsion lowers the binding energy. Have we not? Yeah. Yeah. Honestly, I don't think it's going to come up, but there we are. Okay. Yeah. Algo más. Anything else? Yes. Okay. On. Yep. 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 You're actually not responsible for that yet. But let's say you did need to do it. What they've done here is that they've broken the graph into two sections, right? So we would have our 1s2, 1s2, 2s2, 2p2, right, for the one on the left. Are you good with why that is the electron configuration? Yep. And then we have the other one, which is, what on earth is going on there? Why is that? Oh, have they put it backwards? Yeah. Oh God, just cross that out. I don't even want to deal with that. Okay. Yeah. Okay. Okay, so we have carbon and oxygen. Yeah. Yeah. Yes. Yes, but it also has more protons in its nucleus. The reason I said this is not part of this unit yet is in our next unit, we're going to learn that electron-electron repulsion within the same shell is not particularly a big deal in terms of atomic size. Not compared with the number of protons in the nucleus. But we're not talking about that yet, so I'm just saying ignore that. Okay? Yeah. Yeah. $29. Okay. Uh-huh. It has a higher binding energy? Yeah. So that is true. because it asks which is not true. Yeah, I know. I hate those questions with like not or except or whatever. Yes. Uh-huh. Shielding. I will explain that in our next unit. I have a whole thing on shielding. Okay? Yeah. We'll talk about shielding later. Going. Yes. Yeah. Yes. Yeah, let's do that. Okay. Okay, 15 and 23. Okay, yeah, so I did actually want to talk about this. Hold on. It's probably faster than doing anything else. Why is this so painfully slow? Sorry, I'm just trying to get this like up on the screen somewhere where I can write on it. And it's being very, very painfully slow. Okay. Okay, so we have this first isotope, which has a molar mass of 125 grams. So I'm going to say I've got isotope A, and it's got a molar mass of 125 grams. I have the second isotope, which has a molar mass of 128 grams. And the average mass is 126.8 grams. Now, first of all, molar mass, grams, AMU is just the atomic mass. Okay, it scales 1 to 1, right? So you can read grams, you can read AMU, it doesn't really matter. What I would do is I would say let this be isotope A and let this be isotope B. Let X be the percent of isotope A. And in fact, I'm going to do it one better. I'm going to say let X be the decimal percent of isotope A. Do you guys understand what I mean by decimal percent? It's just where you move the decimal place over 2 places so you don't have to like divide by 100 or whatever. What does that mean then is the amount of isotope B? It's 1 minus X. So what we have then is we have isotope A is X, so I have X times 125 plus 1 minus X times 128 is equal to 126.8. And now we have 125X plus 128 minus 128X equals 126.8. And from here we just do some algebra. Do you want me to do the algebra? Sure, okay. So I now have negative 3x and is equal to 126.8 minus 128. So negative 3x then is equal to, because I should be able to do this in my head, but apparently I cannot. Is it 1.2? Negative 1.2. Hey, look at me, I did do it in my head. Woo! Okay. And so that means I can get rid of those negative signs, right? And then I can go x is equal to 0.4. And let's remind ourselves, what did I call isotope A? I called isotope A the lighter isotope. And we wanted the lighter isotope's percentage, so that is going to be 40%. So that's going to work for any 2-isotope system. I have no idea what you would do if you had 3 isotopes. I'm not going to give you a question like that. That's ridiculous. Yes? Yeah, if you have something that has both diatomic and monatomic data, if you're calculating an average, you can just ignore the diatomic stuff and just do it from the monatomic. Okay? So that was number 15. What else did you want? Number 23. So we have 2 stable isotopes, just 2. How many different masses do we have? I'm just going to call this chlorine 35 and chlorine 37. And people who are doing statistics can probably tell you a faster way to do this, but I'm kind of stupid, so I'm like, oh, I could put 35 and 35 together and that would give me 1. I could put 35 and 37 together and that would give me a second one, and I could put 37 and 37 together and that would give me a third one. So that would just be 3. Did you follow that? No, because I could have chlorine 35 and 35, and that would give me 1 mass. I could have 35 and 37, which would give me a second mass, or I could have 37 and 37. Oh, absolutely. Yes, no problem whatsoever. Yes. So it's asking how many different masses would you have of a molecule of Cl2? So if you've got a chlorine atom with a mass of 35, it could be bonded to another chlorine atom with a mass of 35, which would have a mass of 70. And then you would have another possibility, which would be a chlorine atom with a mass of 35, but it could be bonded to a chlorine with a mass of 37. And that would be 72. And then finally, you could have 237 chlorines bonded together, which would give you 74. And so this would then, that gives you 3 different possible masses for the molecule. Yeah? How many possibilities are there? That's all it's asking. Yeah. 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 Oh, the free response. Multiple choice. Oh, the one I sent you on the weekend? Was that the one I sent you on the weekend? Oh, that one. Yes, yes, yes. Pez. Pez, Pez, Pez. Okay, gotcha. Pez. Pez. Exactly. Yes. 26, 22. Which is funny because you put up a 2 and a 2, and I heard 26, and I'm like, that did not make sense with what your fingers were doing. So I should have listened to your fingers because they made sense. Which peak is produced by the ionization of 5 valence electrons? I'm going to guess A. Am I right? Okay, and the reason I'm guessing A is that I know that they come in groups of either 2, if it's a full S subshell. And then I'm looking at these ones and I'm like, this peak C looks. Okay, sorry. If I had been clever, I would have printed these into OneNote ahead of time, but I hadn't thought that through. And then if I look at C and A, those have got to be P subshells. And C looks to be 3 times higher than D, right? So I'm guessing that that's a P6. And so that means that peak A would contain 5 electrons. Because it's like bigger than B and D and E, which is 2 electrons, but it's not quite as big as C, which is 6 electrons. Huh? Which peak is produced by the removal of 5 valence electrons? Does that sound better? Can we use removal instead of ionization? What? Yes? What? I'm sorry, I'm not understanding. I'm going to get closer so I can hear you better. Okay, today, yes. You have another question? Excellent. Yes, we assume it's in its ground state. Yeah. Yeah. Yes. Yeah. Yes. I mean, that's just a quick way of remembering it if you're not wanting to remember that you remove your outer shell electrons first, like your highest energy level electrons first. It's a mnemonic device. It's not a reason. It's not. Because, yeah, but if we, but for whatever reason, when you take electrons out, you remove them from the highest n value first. Yeah? And I don't exactly know why, but I do know that that is how it works. Even though they go in to the 4s, and then they go into the 3d, and then they go into the 4p, right? That's the order they go in. We put in 2 here, we put in 10 here, we put in, let's just say we put in 2 here. If I form a 2+ ion, these are going to go first. That's easy, right? Because that makes sense. But it would kind of make sense for this to go next, but it doesn't. So if we have a 3+ ion, this one would become 4s1. And then if we have 4+ ion, it would become just 3d2. And I think there's something about stability of a filled D subshell, but like I said, there's contention around that at this point. So I figure if big minds are having contention about it, I should not be teaching it. Yeah. You just need to know that's the order they come out. Yeah. Yes. Highest n, remove from the highest n value first. Always take from the 4. Always add to whichever one comes next. Always add like off bow. Add like off bow. Yeah. Yeah. What's that? Just add like you would normally add for like writing any electron configuration. Yes. Adding is easy. Just put them in like normal. Taking them away, remove from the highest n value first. Yes. Yeah. You are not required to. You don't have to show the thought process, no. For me, I might do it just because like my brain is better that way, but you don't have to by any stretch. Yeah. Yes. Shh. If it doesn't specify, you can write it in core notation, yes. Yes. I don't know. I always think the tests are much shorter than they are. I've written it to be shorter, but you guys seem to take forever. Like, honestly, I really want to encourage you on this test to work as quickly as possible. So, how you do that, because this is going to be a skill that will aid you in all of your AP exams, in all of your university exams, you're going to do this test in 3 passes. Okay? Pass number 1, okay, the first time you go through it, that's what I mean by pass. First time you go through it, you are only going to do the questions that are cheap and easy. Okay? Like, don't do anything that requires any thinking. Cheap and easy marks. Okay? Second pass through, you can do things that are easy, but might require you to do some mental math or like think something through, but you pretty much know what you're doing. It just requires a little more work. Yes? Don't even touch the ones where you have to think about it until you're going through the 3rd time. Yeah? Because you want to get your maximum value of things that you know right up front, right? Because if you spend a lot of time stuck on a question and then you're trying to rush through the ones that you do know, then you're going to have problems with running out of time, right? And you won't get your maximal marks because you're like, oh no. I'll be honest with you. The other thing is too, that by doing it that way, you'll often come across questions that will trigger things for the ones you're having trouble on. You know how you can do that? Like this question will help you with that question and that kind of thing. That's very helpful for that. It also gets the lubrication in your brain moving, right? It's like it's oiling the wheels in your brain, right? So that they're going like, hey, I can do this. I got questions 3, 7, and 14. Woo! Look at me go, right? And you sort of get that little like positive vibe. Honestly, I wrote a physics test. Not that physics test. I actually did not too bad on this one. It was on electricity and stuff like that, and it was my final exam. And I literally looked at page 1 and I was like, oh, I do not know how to do that question. It was about capacitors. I never ever understood capacitors. And then I went to question 2 and I'm like, oh, I don't know how to do that one either. And I kept flipping. I got to question 8, which was the last question on the test. And I was like, I know how to do a question. Like, it was really exciting. So I did the question. I did question 8. I'm like, yes, question 8, fantastic. And then by the time my brain had sort of settled into problem solving mode rather than I don't know how to do this mode, I managed to figure out some of the other ones. I don't think I ever solved question number 1. I might have written down some random things in the hopes of, you know, flinging some things out and getting some marks, which is not always a good strategy, but, you know, but I did okay. I got a B+. B+ in physics. Yes. Thank you. It was super exciting because like physics was like, I mean, I scraped a B- the first term and like, I was so happy to get a B+. I got an A- on one of the midterms. I was so excited. In physics, an A- in physics, but not all over, or not overall. Anyway. So be smart about how you write the test. Just be free to circle questions, put a star beside it. It just means come back to me later. Sometimes you may never come back to it, and that's okay. What should you do if it's a multiple choice and you never come back to it? You can do educated guesses. Educated guesses are good. How do you educate a guess? You eliminate the ones you don't know, you know it's not, and then you guess. What if you can't? What if you know nothing about this question? This is some foreign concept that you've never heard of before. You can do that, but statistically speaking, the answer is B. Okay, so it's not up to date. I've not run a statistical analysis in a few years, but before the new curriculum, statistically, B's beat out C's by a small percentage. B's and C's certainly beat out D's, and A's never guess A unless you've got a really good reason to. People don't like writing A as the answer because it's too obvious. It's like, it's too juicy. It's sitting in front of you, the right answer. So don't do A. Yes. You could, sure. Yeah. Yeah. But I honestly, I don't have a strategy. I just randomly select things from here and there and everywhere. Yeah. I'm a here, there, and everywhere. I have all the old review books. I have all the old exams going back to 1974. You know, like, yeah, they're from everywhere. I do have some tests, and I don't know even what grade it is, but there's like 6 B's in a row. Or D's. Any other questions, test related? All right. Do we need time to work on this today? Okay, tomorrow we can move on to Lewis structures. You don't feel like you need time? You're like, I'm done. I could just, yeah. I would actually like to move on to Lewis structures because no. And you don't mind if we have to cram things more in at the end of January? You're okay with moving faster? They're not on the test. For the next unit. Let's do Lewis. Hey, I'll put it before it. I'll put it in another area. No, I want you to have that one instead of the other one because it's got more stuff. Recycle it. Give it to Andrew.
Thank you. With these worksheets, do you have like for example, would you have like extra of these in like April?
Sure.
Like, would you do you have like
Sure.
11 hours worksheets just lying around?
Would you like me to add you to my class in Teams?
Are they on Teams? Yeah, add me.
Okay. Oh, you also get this, but I'll give that to you afterwards. Okay, so first of all, 3.5E, which is the front page of what you've got. Electron dot notation is a way of representing the valence electrons of an atom with dots. The dots are placed around the element symbol with a maximum of 2 electrons per side. Okay, so maximum is going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. Does that look familiar? Did you do anything like that last year? Yes, okay, good. So you're going to go around the atom, placing dots on all 4 sides alone. Placing dots on all 4 sides, what? Alone, before pairing electrons. So if I was to draw my electrons on there, I wouldn't do it like I just did. I knew I was going for the maximum, so I would go 1. Where would I put number 2? On the right. 3, down. 4, 5, 6, 7, 8. Yes? And what that will do is it will allow the electrons to not be paired until they have to. Does this remind you of anything? Orbitals. So essentially we are stripping down, we're kind of combining a Bohr model with the orbitals, but we're simplifying it, super simplifying it. Okay? Let's use period 2 and see how this works. Now, just before we go on, do you guys know how many valence electrons there are on for every group? Yes? How many valence electrons in group 1? 1. How many in group 2? Now, what do we know about the transition metals? Can we draw Lewis structures for them? No, so we're just going to ignore all the transition metals. How about group 13? How many valence electrons? 3, 14, 15, 16, 6, 17, 17, and 18 has technically 0. Okay, although we would draw 8 electrons on, say, a neon atom. Okay, all right. Now, to be honest, here we go, we've got lithium. Does it matter whether I put the electron here or on the top? Doesn't matter. For beryllium, does it matter if I put the electrons on either side or if I was to do it like this? Does it matter? No. Boron, as long as there's 3 of them on separate sides, it's fine. Are we feeling good about these structures? Okay, very good. So this is the same for all other periods. It doesn't matter what period you're in. If you're in group 16, you have 6 valence electrons. So sulfur, which is in group 16, would have 1, 2, 3, 4, 5, 6. Would it be okay to draw it like this? 1, 2, 3, 4, 5, 6? Yes, it would totally be fine. Okay? Helium is an exception. Why is helium an exception? Because that's the 1s orbital, right? So we're at 1s2. So we are actually pairing them at that point. Now, each atom, of course, likes to have a complete octet. Have we talked about the term octet? Okay, complete octet. When it bonds with other atoms, this is called the octet rule. Oh. Notice that the noble gas atoms, such as neon, already have 8 electrons, so they hardly ever get involved in bonding. What about groups 3 to 12? Transition metals, there's no electron dot notation for those. Okay? Non-bonding electrons are called lone pairs, and they are not involved in making bonds to other atoms. Now, this is a little bit of it's a little bit of an oversimplification, but it'll do for now, and I'll tell you why it's an oversimplification later. So if we have oxygen, we have a pair on the left, we have a pair on the right. Do they need to pair up with anybody? Or are they already paired? They're already paired, so we have 2 lone pairs on the oxygen, and we have 2 little spaces, essentially, yes, where we could put electrons. So normally, oxygen will form how many bonds? Oxygen normally forms 2 bonds. How about chlorine? Take a look at chlorine's Lewis dot structure. It's got 1 little box there. That means that chlorine normally forms 1 bond. And it has 3 lone pairs, which is here, here, and here. Calcium has 0 lone pairs of electrons because nothing's paired, right? They're separate from one another. So Lewis structures are showing in 2 dimensions how the valence electrons are arranged in a molecule. We will go from 2 dimensions into 3 dimensions, but not yet. Lewis structures only show the connectivity of the atoms. They do not tell you anything about the 3D structure. We will eventually get to Vesper theory, which is spelled Vesper, but pronounced Vesper. Which stands for valence shell electron pair repulsion. But like I said, we'll cover that later. Not in section 8. I just stole these notes. Yes? Yep. It just isn't. Just go with it. Okay. And also bear in mind that it is highly unlikely on the AP exam you will be asked to draw Lewis structures of metals, because mostly we're concerned about showing structures of molecules, which are all non-metals. Okay, so exceptions to the octet rule. Hydrogen obviously only wants 2, because it would be full once its first shell has 2 electrons. There are 3 others, and I say this is like, you know how sometimes you'd call basketball b-ball? Okay, b-ball. Oh, look, b-ball, b-ball. And how many people are on a basketball team? I don't know, but I know it's less than 8. Oh, I don't know. Honestly, I don't know. How many people are on a basketball team? I just on the court, on the court. How many people on the basketball team? It's less than 8. And so B-ball needs less than 8 electrons. Yes? Less than 8. So I know. But I was desperate for some way to make this memorable. So we have beryllium, which only needs 4. And we have boron and aluminum, which needs 6 and 6. Okay? Because it does. Okay? Now, expanded octets, and we will talk about these, but not for a little while. If you're in period 3 and lower, what do we get in period 3 and lower? What's present in period 3 and lower that isn't present in the other, in periods 1 and 2? D orbitals. So what we will have is we will actually have, we're in shell number 4, right? Or sorry, we're in shell number 3 when we're in period number 3. But are there any 3Ds in period 3? No, because they don't start until period 4. So there is an empty 3D subshell in period 3 that's not being used at all. So if you want to cram extra electrons in there, you can do it. Okay, same thing for if you've got period 4. Period 4 contains the 3D subshell, which is all filled up now, yes? But it doesn't have any electrons in the 4D subshell, so it can actually accommodate extra electrons. Do you need to be able to explain that? No, you don't, but it might help you remember that that's why you can have more than 8 electrons. That's what they mean by expanded octet. You can sometimes have more than 8 shared electrons around them. Not 18, you'll usually end up with either 10 or 12. Okay? We'll worry about those a little bit later. We're not going to deal with those today. Okay? But those are the exceptions to the octet rule. Hydrogen only needs 2. Beryllium needs 4. Boron needs 6, and aluminum needs 6. So it's basically 2, 4, 6. 2, 4, 6, 6, and then we get to 8, and then we have like period 3 and lower can do what? Can have either 10 or 12. They can have 8 or 10 or 12. Okay. Does it matter? No. Okay, we're moving on. Rules for drawing Lewis structures. We are going to list the 5 rules and there's examples in here. I'm actually going to do the examples off to the side. I put them in here in case somebody is away and they're not like taking the notes along with us. Okay, so you might want to have scrap paper. Okay, so if you want, there's free blank paper back there. You might want to grab it. Now, before we start, we need some important points. Hydrogen and fluorine only make one bond, ever. Hydrogen and fluorine only one bond, ever. Iodine, bromine, and chlorine, only one bond usually. Okay? What period is hydrogen in? Period 1. What period is fluorine in? Period 2. What about I, Br, and Cl? 5, 4, 3. So they're in 3, 4, and 5. What is magical about periods 3, 4, and 5? They have empty d subshells, so maybe every once in a while we can cram some extra electrons onto them, which is why maybe sometimes they can have more than one bond. Okay? Do not put more than 4 bonds on the central atom unless the atom is in period 3 or lower. Okay, so carbon should never have more than 4 bonds. Okay, because it's not in period 3 or lower. A bond, which we draw as a line, counts as how many electrons? 2 electrons. All right, and now we have the rules. And I'm actually going to write them over here, and we're going to do an example, CH3I. And actually, I'm not even going to do that. I'm going to give you a lovely copy of the rules. So you can have them in front of you and refer to them as we go along. On the front of this page is the simplified version. On the back of this page is like more structures all written out. Okay? 1, 2, 5. I'm trying to count them, but my fingers aren't sticking to the paper, so if you end up with too many, just bring them back. If you have extras, please just count them back. I was unable to separate them because I can't lift my fingers. Not gross. Okay, step 1. Count the valence electrons. So you're writing on paper. Well, you can, but like you don't have to write it down, but don't look at it. Okay? Don't look at it on the paper because you want the process to happen as we go along. It's written there in case, like, say you were away or whatever. You don't have to write this down. You can just like watch and absorb if you want to. So we're going to count the valence electrons. We have 1 carbon, we have 3 hydrogens, and we have 1 iodine. So that's going to be 1 times, how many valence electrons does carbon have? 4. So that's 4 valence electrons. Hydrogen, we have 3 of them. How many electrons, valence electrons, does hydrogen have? 1, so that is 3 valence electrons. And iodine, we have 1 of them. How many valence electrons? 7, so that's 7 valence electrons. Obviously, you would not have to write down VE every time. I'm just kind of being a little bit like I'm over explaining a little bit because it's our first time through. Okay, so now we have 7 plus 7 is a total of 14 valence electrons. Okay. Step number 2. We are going to draw a skeleton structure. In a skeleton structure, you want to put the least, there's a few ways of deciding who goes in the middle. Carbon goes in the middle. Why does carbon go in the middle? Because it can form 4 bonds, right? So in the middle, always carbon, if it's there. Yes, Elliot. Yeah, although silicon doesn't tend to form a lot of molecules, not in the same way that carbon does. Now, you are also going to, if there's not any carbon, you can put the least electronegative in the middle. Now, remind me about the electronegativity trends. Up in this corner, electronegativity, is it high or low? That is high. And down here, electronegativity is low. Okay, so going to the right, we have electronegativity increases, and going down, electronegativity decreases. Okay. Also, you are going to try and make this structure as symmetrical as possible. Don't try too hard. Like, it's usually pretty obvious, the correct structure, okay? It only gets a little funky if you have more than one central atom, right? Like if you got like C2H6, right, or something like that, it gets a little funky. But our skeleton structure then, I'm going to draw it over here so that we can see everything all at once. Who's going to go in the middle? Carbon. And then we are going to draw lines, each of which represents a single bond. And how many electrons does that represent? 2 electrons. And then we're going to attach our other things. Hydrogen, hydrogen, iodine, hydrogen. Does it matter where I put the iodine? Nope, you can put it wherever you like. So that is our skeleton structure. Step number 3, add lone pairs to give everybody a complete octet unless they are an exception. Yeah, so our exceptions, if you recall, are hydrogen and B, ball. Okay. So this is 2, 4, 6, 6. So do we have any exceptions here? Hydrogen. But hydrogen is almost so ubiquitous that we stop even worrying about it as an exception at some point. We're just like, what? Ubiquitous. It means everywhere all the time. Ubiquitous means it's always there, it's popping up in your face, it's like always in front of you. No, it's just an English term. Yeah, ubiquitous. Was it going to have a KW? Ubiquitous. Yeah. I'm not very good at defining words, but that's kind of what it means. So hydrogen is everywhere all the time. You're not even going to have to think that it needs 2 electrons. You're just going to be like, I am not throwing any electrons on hydrogen. Okay? Who does need some lone pairs in order to give it 8 electrons? Iodine. Does carbon need any lone pairs? No, because it's already got 2, 4, 6, 8 in the bonding pairs. Yes? So we do need to do it for iodine. Where do we put those electrons? 2, 4, 6 electrons. Okay? So that's step 3. Step 4, we're going to count and check the number of electrons. So we're going to count the electrons and check it against the number in step 1. So you can just go around and tap on them and be like 2, 4, 6, 8, 10, 12, 14. Or you can write down, you can be like, I have 4 lines. So that's 4 times 2, which is 8 electrons. I have 3 lone pairs. So that's 3 times 2 is 6 electrons, and that gives us 14 electrons. The only reason I would recommend it doing it this way is if you have a more complicated structure and it's hard to count them, or if you're one of those people who like loses track, right? You're like 2, 4, 6. Oh shoot, did I count those ones already? You know what I mean? That would be a reason for doing it this way. And then we go and we say, does this match step 1? Yes. And if that's the case, and if it's not an ion, you are done. Yes. You will show ionic in a completely different way. I'll show that to you later. Okay? And I don't think AP is going to focus on ionic, but I'll show it to you just in case. Okay? So that is one structure. What if I gave you, what's another one? What's another good one? NH3. What is the name of NH3, by the way? That is ammonia. What's the first thing you do? Count the valence electrons. So nitrogen has, how many does nitrogen have? 5. And hydrogen has 3 times 1, so we have 5, and 3 gives us 8. What would our skeleton structure look like? What would our skeleton structure look like? And does it matter where I put the lines? Can I put it up top, or should I put it at the bottom, or does it matter? It really doesn't matter. I'm going to do it this way just for now, but it doesn't matter. So that was step 1. Step 2 was my skeleton structure. Step number 3, we are going to add lone pairs until what? Until everybody has an octet. Where do we need to add a lone pair? Below the end, there we go. What is step 4? Count and check. Count and check the electrons. So if we count, we have 3 bonds. So that's 3 times 2 is 6 electrons. We have 1 lone pair. So that's 2 electrons. And that gives us 8 electrons. Are we done? Is it an ion? It's not an ion. So we would be done at this point. You can go home and study. Did you need a printout of that other review, or are you happy doing it online? Printout? I will print it out right this second, okay? I will be right back.
I don't get the B-ball.
You don't get what?
The B-ball.
Don't worry about it. We'll talk more about it tomorrow. Yeah. Matthew, there's nothing to get. It's just that if you have boron, only give it 6 electrons. That's it. There's no reason. Just go with it. I mean, there is kind of a reason, and I'll teach you later, but just for now, just be like, B-ball. I can just remember that. It can only have 6 electrons on it. It will not have 8. Yeah. Hi.
It's just, in that case, I don't have to give it an offset. I can give it that many.
Just give it that much. That's it. Yep.
Because I thought whichever one's further but in this case, like,
Lowest energy Bohr orbital, so that's the lowest energy value. Lower standard value. Yeah.
Okay, and lower standard value would be 10, 11.
Yes.
On Wednesday,
Yes.
we have to go to the grade 8 retreat.
Okay.